When we say that the speed of light is the ultimate limit in the universe, we are not really talking about light at all. We are talking about how reality preserves order. The deepest meaning of this limit is that cause must come before effect, and that the universe has a built-in mechanism to make sure this sequence is never violated. Richard Feynman understood this with extraordinary clarity. He realized that the speed of light is not an arbitrary number discovered by measuring beams in a laboratory, but a structural feature of the universe that protects logic itself. Imagine a universe with no speed limit. In such a universe, information could travel infinitely fast. If something happened in one place, its consequences could appear elsewhere instantly or even earlier than the event itself, depending on how motion and time are defined. At first glance, this might sound like a convenience rather than a problem. But when you follow the consequences carefully, the entire idea of cause and effect begins to collapse. You could see the result of an action before deciding to take that action. You could receive a warning about an accident and use that warning to prevent the accident from ever happening, which would then erase the reason the warning existed in the first place. The universe would be filled with logical loops that have no consistent resolution. Feynman emphasized that physics is not just about predicting numbers. It is about preserving consistency. A universe that allows effects to precede causes cannot maintain a stable notion of reality. Time would lose its meaning as a direction. Events would no longer form a coherent narrative. Instead of a flowing story from past to future, the universe would resemble a scrambled manuscript where pages appear out of order and sometimes rewrite themselves. The speed of light acts as the boundary that prevents this chaos. It defines how fast causal influence can propagate. If one event is to influence another, that influence must travel no faster than this limit. As a result, the structure of time remains intact. The past can influence the future, but the future cannot reach backward and alter the past. This may sound obvious from everyday experience, but it is far from trivial at the fundamental level. Nature enforces this rule with extraordinary precision. What makes this even more astonishing is that the limit applies to everything, not just light. Gravity, electromagnetic interactions, nuclear forces, and even quantum correlations are constrained by this maximum speed when it comes to transferring usable information. Light merely reveals the limit because it happens to move at that speed. If light were slower, the limit would still exist, and light would simply fall below it. Feynman often pointed out that space and time are not independent arenas. They are interwoven into a single structure. When something moves through space, it also moves through time, and the faster it goes through space, the slower it progresses through time relative to something at rest. This is not a philosophical statement. It is a measurable fact confirmed by experiments involving fast, moving particles and precision clocks. The speed of light emerges naturally from this geometry of spacetime. It is the speed at which movement through space consumes all available movement through time. At that boundary, something remarkable happens. For an object moving at the speed of light, time effectively stops. From the object's own perspective, if such a perspective could be meaningfully defined, no time passes between its emission and its absorption. This is not a poetic exaggeration. It follows directly from the equations of relativity. Feynman found this idea both beautiful and unsettling, because it shows that time itself is flexible, yet governed by strict limits. Now consider what would happen if something could exceed this speed. Faster, then light motion would imply traveling in such a way that time reverses direction for some observers. In certain frames of reference, an effect would appear before its cause. This is not a matter of interpretation or illusion. It is a direct mathematical consequence of the way spacetime transformations work. Feynman stressed that physics must be consistent in all frames of reference. If a law works for one observer but produces contradictions for another, it cannot be fundamental. This is why the speed of light is not just a speed limit, but a safeguard. It ensures that all observers, no matter how they move, agree on the order of causally connected events. They may disagree on how long events take or how far apart they are, but they will never disagree on which event caused which. This shared agreement is what allows the universe to function as a coherent system rather than a collection of conflicting viewpoints. Energy plays a crucial role in reinforcing this limit. As an object accelerates and approaches the speed of light, its energy increases dramatically. This is not because the object becomes heavier in some simple mechanical sense, but because the relationship between energy, momentum, and velocity becomes increasingly steep. Each additional push yields less increase in speed than the one before. Near the speed of light, enormous amounts of energy produce almost no additional velocity. To cross the limit would require infinite energy, which is another way nature says that such a crossing is impossible. Feynman loved this kind of explanation because it shows how different aspects of physics cooperate to enforce a single rule. Relativity sets the geometric constraint, energy conservation makes the cost prohibitive, and causality provides the logical necessity. The limit is not imposed from outside the system. It emerges from within the system itself. Even quantum mechanics, which often seems to defy common sense, respects this boundary in subtle ways. Quantum entanglement can create correlations between distant particles that appear instantaneous, but these correlations cannot be used to transmit information faster than light. Feynman was keenly aware of this distinction. Nature allows strange connections, but it draws the line at usable cause and effect signals. The universe permits mystery, but not contradiction. From a documentary perspective, what is most striking is how this limit shapes everything we observe. Stars shine the way they do because energy moves outward at finite speed. Galaxies have structure because gravitational influences propagate at this limit. Even our view of the cosmos is a journey into the past because light takes time to reach us. The speed limit does not merely constrain motion, it sculpts reality across vast scales. Feynman often reminded people that the universe is under no obligation to be simple or comfortable. Yet the speed of light limit is both profound and economical. One rule, applied everywhere, preserves the arrow of time, the integrity of cause and effect, and the possibility of knowledge itself. Without it, prediction would be meaningless. Science would collapse, because experiments rely on the assumption that causes produce effects in a reliable order. In the end, the speed of light is not about how fast we can travel. It is about how the universe tells its story. It ensures that the story unfolds one frame at a time, never jumping ahead of itself, never rewriting its own beginning. Feynman saw this not as a restriction, but as a triumph of coherence. The universe, vast and strange as it is, follows rules that allow it to exist without logical contradiction. The speed of light is the quiet, unbreakable rule that keeps time moving forward and reality intact. When Richard Feynman spoke about limits in nature, he was never satisfied with the idea that a rule exists simply because we have not yet found a way around it. He wanted to know whether a limit was artificial or fundamental. In the case of the speed of light, he was convinced it belonged to the deepest category possible. This limit does not arise from weak engines, fragile materials, or incomplete theories. It arises because space and time themselves are constructed in such a way that going faster would tear apart the logic of the universe. The speed of light is not a wall placed at the edge of reality. It is the shape of reality itself. To understand this, Feynman urged people to abandon the instinctive idea that space is a passive stage, and time is a universal ticking clock. In everyday life, time feels absolute. Everyone seems to share the same now, but experiments show this is an illusion. Two observers moving relative to one another do not agree on what events happen at the same time. This is not a flaw in measurement. It is a property of the universe. The faster you move, the more your sense of simultaneity shifts. At first, the effect is tiny, invisible in daily experience. But as speeds increase, the disagreement becomes dramatic. The speed of light sits exactly at the point where this disagreement becomes unavoidable. It is the speed at which the structure of spacetime forces all observers to agree that something cannot be overtaken. Light defines the maximum slope of cause and effect in the universe. Feynman explained that instead of imagining objects moving through space over time, it is better to imagine events laid out in spacetime, connected by lines of influence. These lines can tilt depending on the observer's motion, but they cannot tilt beyond a certain angle. That angle corresponds to the speed of light. What makes this revelation so unsettling is that it means speed is not just about motion. It is about geometry. Just as there is a fixed ratio between the circumference of a circle and its diameter, there is a fixed relationship between space and time. The speed of light is the conversion factor between them. It tells us how many units of space are equivalent to a unit of time. Change that number, and the entire structure of physics collapses. Energy, momentum, mass, and even the identity of particles would no longer fit together consistently. Feynman loved to point out that light's role in this story is almost accidental. Light happens to have zero rest mass, which forces it to travel at the maximum possible speed. If some other massless particle existed instead, it would play the same role. Light is not special because it is fast. It is fast because it is special in the way spacetime treats massless things. This subtle inversion of cause and explanation is a classic Feynman insight. It teaches us not to confuse symptoms with principles. As objects approach the speed of light, space and time begin to behave in ways that defy intuition. Lengths contract in the direction of motion. Clocks slow down. These effects are not distortions caused by faulty instruments. They are real changes in how spacetime measures itself. Feynman emphasized that there is no preferred viewpoint from which these changes are really happening. Each observer is entitled to consider themselves at rest. The laws of physics must look the same to all of them. This demand for symmetry is what locks in the speed limit. If faster than light motion were possible, this symmetry would shatter. One observer could see a signal arrive before it was sent, while another would see the same signal moving backward in time. The concept of a universal law would dissolve, replaced by observer-dependent contradictions. Feynman was adamant that this cannot be how nature works. Physics, to be meaningful, must give consistent answers regardless of who is asking the question. Energy again plays the role of enforcer. As speed increases, energy and momentum intertwine more tightly. The familiar equation that relates energy and mass reveals that mass itself is a form of energy. This means that pushing an object faster effectively adds to its energy content. Near the speed of light, the amount of energy required becomes so large that it dominates all other considerations. No finite process can supply infinite energy, so the limit remains intact. Nature does not forbid faster motion by decree, it makes it unattainable by design. From a quantum perspective, this limit becomes even more intriguing. Particles are described by wave-like equations that spread out through space and time. These equations respect the same maximum speed. Disturbances in quantum fields propagate no faster than light. Even virtual particles, which seem to appear and disappear freely, cannot transmit information beyond this boundary. Feynman, who helped pioneer quantum electrodynamics, was deeply aware of how delicately balanced these theories are. Remove the speed limit, and the mathematics stops making sense. There is also a philosophical weight to this idea. The speed of light forces the universe to have a local structure. What happens here depends primarily on what happened nearby in the recent past, not on distant events happening now, somewhere else. This locality is essential for complexity. Without it, every part of the universe would be instantly entangled with every other part in a way that eliminates meaningful structure. Stars, planets, and life itself rely on the fact that influences take time to travel. Feynman often framed this in terms of information. Information is physical. It requires energy to move, store, and process. The speed of light is the maximum rate at which information can be transmitted. This ensures that the universe cannot update itself all at once. It must evolve step by step. Each moment grows out of the previous one, constrained by the finite speed at which information flows. From a documentary lens, what stands out is how deeply this single limit penetrates reality. It shapes the evolution of the universe from the earliest moments after the Big Bang. It determines how quickly galaxies form, how stars burn, and how signals reach our telescopes. It even affects our own bodies, as the electrical signals in our nerves are ultimately governed by electromagnetic interactions that obey this rule. Feynman saw elegance in this. The same constant that governs light also governs time dilation, energy conversion, and the structure of spacetime. It is not an arbitrary speed chosen by nature at random. It is the glue that holds physical law together. Remove it, and the equations unravel. Keep it, and the universe remains coherent, predictable, and astonishingly rich. In this sense, the speed of light is not a constraint imposed on an otherwise free universe. It is the principle that makes freedom meaningful. Within this limit, particles can dance, fields can fluctuate, and complexity can arise. Beyond it, nothing sensible can exist. Feynman understood that the true wonder of physics is not that there are limits, but that those limits are so perfectly tuned to allow a universe that works at all. When Richard Feynman explored the idea of limits in physics, he often returned to a deceptively simple question: what would actually go wrong if a fundamental rule were violated? The third keynote centers on the way relativity, quantum mechanics, and energy unite to make the speed of light an unavoidable boundary. This is not a coincidence of separate theories agreeing by chance. It is a convergence that reveals something profound about how nature is built. Each framework approaches the problem from a different angle, yet all arrive at the same conclusion. There is a maximum speed, and crossing it would unravel reality. Relativity provides the geometric backbone of this limit. Space and time are not containers in which events happen independently. They are aspects of a single structure. Motion through one affects motion through the other. Feynman emphasized that this is not philosophy but measurement. When particles move at high speeds, their lifetimes extend, their clocks slow, and their paths through spacetime curve in predictable ways. These effects have been tested countless times in accelerators and satellites. The equations describing them are unforgiving. They leave no room for exceptions. Quantum mechanics, on the surface, appears more permissive. It allows particles to behave like waves, to exist in multiple states at once, and to be correlated across vast distances. But beneath this apparent freedom lies a strict discipline. The equations governing quantum fields contain the same speed limit. Disturbances cannot propagate instantaneously. Even the probabilistic nature of quantum events respects causality. Feynman was deeply aware of this because he helped build the mathematical tools that make these predictions possible. Energy binds these theories together. In relativity, energy and mass are interchangeable. In quantum mechanics, energy comes in discrete packets. In both, energy constrains motion. As an object accelerates, its energy increases. As its energy increases, its resistance to further acceleration grows. This is not friction or mechanical wear. It is a structural property of spacetime. The closer you push an object toward the speed of light, the more the universe pushes back. Feynman delighted in pointing out that this resistance is not arbitrary. It is precisely calibrated. The equations ensure that no matter how clever the method, no matter how exotic the technology, the barrier cannot be crossed. This is why physicists do not seriously search for engines that exceed the speed of light. The problem is not practical, it is conceptual. The universe has no consistent way to describe such motion. Consider what would happen if this balance were broken. If quantum mechanics allowed information to travel faster than light, entanglement could be used to send messages backward in time. If relativity allowed faster motion, different observers would disagree on the sequence of events in ways that lead to contradictions. If energy did not increase without bound near the limit, nothing would prevent objects from accelerating endlessly. Each theory alone warns of trouble. Together, they make the warning impossible to ignore. From a documentary perspective, this convergence is one of the great achievements of 20th century physics. It shows that our most successful theories are not isolated islands. They are parts of a single, interconnected map. The speed of light sits at the center of this map, linking geometry, probability, and energy into a coherent whole. Feynman often used analogies to make this idea tangible. He compared the speed limit to the edge of a chessboard. The rules of chess make sense only within the board. Try to move a piece beyond the edge, and the game itself loses meaning. Similarly, the laws of physics make sense only within the bounds set by the speed of light. Beyond it, the concepts of time, energy, and causality no longer fit together. This limit also explains why the universe has a certain texture. Events are local. Changes propagate outward, not instantaneously, but at a finite rate. This allows patterns to form. Stars can ignite, burn, and die without immediately affecting distant galaxies. Information takes time to spread, creating layers of cause and effect. Complexity thrives in this environment. Life, in particular, depends on it. Biological processes rely on signals traveling at finite speeds, creating delays, feedback loops, and stability. Feynman saw beauty in the way quantum uncertainty fits into this picture. Uncertainty does not mean chaos. It means probabilities governed by strict rules. The speed of light ensures that these probabilities evolve smoothly over time. Without the limit, quantum fluctuations could influence distant regions instantly, erasing the distinction between near and far. the universe would lose its sense of scale. Energy conservation plays a quiet but decisive role here. It ensures that processes do not create something from nothing. Combined with the speed limit, it prevents runaway effects. A small event cannot instantly trigger infinite consequences. Everything unfolds at a controlled pace. This restraint is not a limitation on creativity. It is a framework that allows structure to exist. In reflecting on this, Feynman often reminded audiences that physics is not about satisfying human expectations. It is about discovering how nature actually works. The fact that three very different theoretical frameworks agree on the same limit is not disappointing. It is astonishing. It suggests that we are touching something fundamental, something that cannot be altered without destroying the entire edifice. From the earliest moments of the universe to the behavior of subatomic particles, this limit has been in place. It shaped the expansion of space, the formation of matter, and the emergence of complexity. It continues to shape our observations today. When we look at distant galaxies, we are seeing them as they were long ago, not because of a technological delay, but because the universe itself enforces patience. Feynman's genius lay in his ability to see unity where others saw complication. The speed of light is not an isolated curiosity. It is the point where relativity, quantum mechanics, and energy conservation meet. Each theory supports the others, forming a self-consistent picture. Remove one pillar, and the structure collapses. Keep them together, and the universe remains intelligible. In the end, this keynote reveals that the speed of light is not a barrier imposed from the outside. It is the natural consequence of a universe that respects geometry, probability, and conservation. It is the reason physics works as a coherent discipline rather than a collection of disconnected rules. Feynman understood that this coherence is the true miracle, and that the speed of light is its most visible signature. There is a quiet rule underlying everything that happens in the universe, a rule so fundamental that we rarely notice it because it has never been broken. That rule is that reality must remain logically consistent. The fourth keynote focuses on this idea. The speed of light is the guardian of consistency, the invisible boundary that prevents time, information, and reality itself from tearing apart. Richard Feynman understood that without this limit, physics would not merely become strange. It would become impossible. Imagine a universe where information could move faster than light. At first, it sounds empowering. Instant communication across galaxies, immediate reactions to distant events. But when examined carefully, such a universe would collapse into paradox. Messages could be received before they were sent. Decisions could be influenced by outcomes that have not yet occurred. The concept of before and after would lose meaning. Feynman emphasized that this is not science fiction speculation. It is a direct consequence of how time behaves when different observers move relative to one another. Time is not a single, universal river flowing identically for everyone. It is personal, shaped by motion and gravity. Two observers can disagree about which events happen first, and both can be correct within their own frames of reference. What saves reality from contradiction is that all observers agree on one thing. If one event can cause another, the cause always comes first. The speed of light is what enforces this agreement. It draws a line that causal influence cannot cross. If that line were crossed, the disagreement between observers would become fatal to logic. One observer would see a cause producing an effect. Another would see the effect appearing before the cause. Both descriptions would be equally valid according to the laws of physics, and yet they would contradict each other. Feynman argued that this cannot be allowed. A fundamental theory must describe a universe that makes sense from every viewpoint. This is why faster than light travel is not merely difficult, it is forbidden by consistency. The universe does not tolerate contradictions. It resolves potential paradoxes by preventing the conditions that would create them. The speed of light is the mechanism by which this prevention operates. Information lies at the heart of this discussion. Information is not abstract, it is physical. It requires energy, carriers, and time to move. Whether it is a photon, a gravitational wave, or a quantum excitation, information must travel through spacetime. The speed of light is the maximum rate at which this transfer can occur. This ensures that the universe updates itself gradually, not all at once. Feynman often highlighted how deeply this limit is embedded in everyday reality. When you see an object, you are seeing light that left it moments ago. When astronomers observe distant stars, they are looking into the past. The universe presents itself to us not as it is now, but as it was when information had time to reach us. This delay is not a flaw. It is a feature that preserves order. Consider what would happen without it. If information were instantaneous, the universe would have no hidden interiors. Every event would be immediately known everywhere. There would be no meaningful separation between here and there. Systems could not evolve independently. Everything would be locked into a single, instantaneous state. Complexity would vanish. Causality is what allows complexity to grow. Small causes produce local effects, which then spread outward. This layered structure gives rise to patterns, feedback loops, and stability. Stars form because gravity pulls matter together gradually. Life emerges because chemical reactions proceed step by step. Consciousness arises because signals in the brain take time to travel and interact. All of this depends on the finite speed at which influences propagate. Feynman also understood that the speed limit protects time itself. Time travel into the past is not just technologically challenging, it is conceptually destructive. If the past could be changed, the present would lose its foundation. The speed of light blocks the paths that would allow such changes. It seals the past from interference by the future. Quantum mechanics sometimes tempts us to think otherwise. Entangled particles seem to respond to each other instantly, but Feynman was careful to distinguish correlation from communication. Entanglement does not allow controllable signals to pass faster than light. It preserves causality even while challenging intuition. Nature flirts with mystery, but it never crosses into contradiction. From a documentary perspective, this reveals an extraordinary design. The universe is flexible enough to allow uncertainty, relativity, and complexity, yet rigid enough to prevent logical collapse. The speed of light is the balance point. It allows time to stretch and space to bend, but not so much that cause and effect lose their order. Energy again plays a role here. To send information faster, one would need to manipulate energy in ways that violate conservation. Infinite energy requirements appear as a warning sign. They signal that the proposed process is not physically meaningful. Nature does not allow shortcuts that undermine its own structure. Feynman often remarked that the beauty of physics lies not in unlimited freedom, but in constrained possibility. The rules are strict, yet within them lies immense richness. The speed of light is one of those rules. It limits what can happen, but in doing so, it makes everything that does happen coherent. When viewed this way, the speed of light is not a disappointment to explorers or dreamers. It is the reason, exploration, and dreaming are possible at all. It ensures that journeys have beginnings and endings, that stories unfold in sequence, and that knowledge accumulates rather than contradicts itself. In the final analysis, the speed of light is the universe's promise to itself, a promise that time will not tangle, that causes will not chase their own effects, and that reality will remain understandable. Feynman saw this not as a restriction imposed from above, but as a deep principle arising from the demand for consistency. The universe obeys this limit because without it, there would be no universe worth describing.